Hello everyone. Let's start today with an interesting thought. Why does ice remain as ice even when a glass of water sits beside it at room temperature? The answer lies in the fascinating concept of equilibrium in physical processes.
At equilibrium, opposing processes occur at the same rate, creating a perfect balance. For example, melting and freezing of ice, or evaporation and condensation of water, continue simultaneously, yet the overall amounts of solid, liquid, or gas remain unchanged. Remember, this state is not static, particles are still moving, but the macroscopic properties like pressure, temperature, and concentration stay constant. This is the beauty of physical equilibrium, and it is most commonly seen in phase transformations such as solid to liquid, liquid to gas, and even solid directly to gas. Now let's take a closer look at solid-liquid equilibrium. Imagine ice cubes floating in a glass of water at 0 degrees Celsius or 273 Kelvin under 1 atmosphere pressure. At this point, the molecules of water are continuously leaving the ice surface and entering the liquid, while at the same time molecules from the liquid are freezing back into ice. This constant two-way traffic keeps the system stable. The temperature at which this happens is called the normal melting point or the freezing point of water. So, when we say water freezes at 0 degrees Celsius, what we actually mean is that ice and liquid water coexist in a dynamic equilibrium where both melting and freezing occur at equal rates. Let's move on to the liquid-vapor equilibrium. Have you noticed how the level of water in a closed container eventually stops decreasing even though evaporation continues? That's because equilibrium is reached when the rate of evaporation equals the rate of condensation. The pressure exerted by vapor molecules in this state is called equilibrium vapor pressure. For water, this vapor pressure increases as the temperature rises, which is why clothes dry faster on a hot sunny day. To give a chemical expression, liquid water in equilibrium with its vapor is written as H2O liquid H2O vapor. Different liquids have different vapor pressures at the same temperature, which explains why acetone evaporates much faster than water. The higher the vapor pressure, the more volatile the liquid. Some solids skip the liquid phase altogether and directly convert into vapor. This is sublimation. Take iodine, for example. If placed in a closed vessel, iodine crystals slowly give off a violet-colored vapor. Over time, the intensity of the color increases until a balance is reached where the rate of sublimation equals the rate of deposition back onto the solid. At this point, the system has achieved equilibrium. The chemical representation is I2 solid I2 vapor. Another common example is camphor, which slowly disappears from a cupboard due to sublimation into the air. Such equilibria show us that even solids and vapors can exist in perfect balance without involving a liquid phase. Now let's discuss equilibrium in dissolution. Think about making a sugar solution. At first, sugar crystals dissolve quickly, but as the solution becomes saturated, no more sugar seems to dissolve. In reality, there's a dynamic equilibrium at play. Sugar molecules continue to dissolve while an equal number crystallize back, maintaining balance. We express this as sugar solid, sugar aqueous. Gases too show dissolution equilibria, like when carbon dioxide dissolves in soda water under pressure. Once the bottle is opened, the pressure is released and the gas escapes. According to Henry's law, the concentration of a gas dissolved in a liquid is directly proportional to the pressure of the gas above it. That's why soda goes flat when left open, as the equilibrium shifts to release carbon dioxide back into the air. Here's a deeper look at vapor pressure and boiling point. At 1 atmosphere pressure, or 1.013 bar, water boils at 100 degrees Celsius. Why? Because at this temperature, the vapor pressure of water equals the external atmospheric pressure. Now, if you travel to a hill station, the atmospheric pressure is lower, so water boils at a lower temperature. This explains why cooking takes longer at higher altitudes. Food simply doesn't reach the same high temperatures before boiling begins. In simple terms, boiling point is the temperature at which liquid and vapor phases coexist in equilibrium with the external pressure. Remember this equation-like idea: boiling occurs when vapor pressure equals atmospheric pressure. Let's wrap up with the key features of physical equilibrium. First, equilibrium can only be attained in a closed system at a constant temperature. Second, the opposing processes such as melting and freezing, evaporation and condensation, dissolution and crystallization occur simultaneously and at the same rate. Third, measurable properties like temperature, pressure, and concentration remain constant once equilibrium is reached. Finally, parameters like vapor pressure, melting point, or solubility act as indicators of how far a physical process has proceeded before balance was established. So in short, physical equilibrium is not about stillness, it's a dynamic dance of molecules happening invisibly, yet giving us stable and predictable conditions in our everyday world. So to sum up, equilibrium in physical processes is a dynamic balance. Ice and water, vapor and liquid, solute and solution all exist in harmony when the rates of forward and reverse changes are equal. I hope this session gave you clarity and made you see equilibrium not as a dull theory but as the secret rhythm of nature itself. Until next time, keep observing the hidden chemistry around you.